Hello students! We are going to start this course with Chapter 1 from your Physics Intermediate textbook. We will start with something very fundamental to this subject, mainly quantities and units. There are those called base quantities, since these are the building blocks of all the other quantities. In other words, all the other quantities are derived from the basic ones and are hence called derived quantities. We find 7 base quantities, and their respective units are called base units. As shown in this table, these are mass, length, time, electric current, temperature, amount of substance, and luminous intensity. The units are shown according to the so-called SI system, and we are going to stick to the system whenever we work out physics problems. So mass should always be input in kilograms in all formulae, length in meters, time in seconds, electric current in amperes, temperature in kelvins, amount of substance, moles, and luminous intensity, candelas, even though you will not be using this last quantity. And these are the symbols for each unit. As we said, all the other quantities are called derived quantities, since these are derived from the 7 basic ones. And here are a few examples of derived quantities. For example, velocity is a derived quantity, and its derived unit is meters per second by definition, since velocity is defined as the rate of change of displacement, so we get displacement on time, so meters per second. The symbol is like this, or this index notation is preferred, where we use the negative power to indicate that the unit is in the denominator. So we get meter s to the power of -1. Acceleration is also a derived quantity, and by its definition, it is the rate of change of velocity. So we get meter per second, so meter per second squared, or m s to the power of -2. Okay, so as we said, we are going to stick to this way of writing units rather with the all over sign. Force, another derived quantity with the unit Newton, simple capital N. Now, what are the base units equivalent to the Newton? So in other words, can we express the Newton in terms of the base units? And the answer is yes, because as we said, the force is a derived quantity, so we can derive it in terms of the 7 basic ones. And here is how. So we know that the equation from Newton's second law, we get F is equal to ma. Now the force in newtons, the mass in kilograms, and the acceleration in meter per second squared. So the Newton is equivalent in base units to kilogram meter per second squared. So kilogram times meters times seconds to the power of -2. So the Newton expressed in base units is kilogram meter per second squared. Of course, we will not be using these units for calculating the force. We will stick to the Newton, but you may encounter questions where you are asked to express the Newton in terms of base units. And this is how it is done. So you have to remember the definition or an equation that allows you to express the quantity, such as the force, in terms of the base units. Another example is energy, which, as you know, is measured in joules. Now, what are the base units equivalent to the joule? One of the results for energy is that for the potential energy. So the potential energy, as you know, is equivalent to mgh, where m is the mass, g is the acceleration due to gravity, and h is the height. Now the mass is in kilograms, g being the acceleration due to gravity, so it takes the units meter per second squared, and h being the height is in meters. So we have kilograms, meter times meter gives us meter squared, and then we still have the second to the power of -2. So we end up with the joule, which is equivalent to kilogram meter squared second to the -2, just as we had on the table, joules equivalent to this. Now, some of you might tell me, what if we start from kinetic energy equals half mv squared? And yes, we can start from that result as well. Now, one thing to note is that we have this constant, half, which is called a dimensionless constant. Dimensionless constant means that it has no units. So, for the sake of this exercise, we simply ignore it. Now, we do repeat the same steps. So the mass is in kilograms. And now we have the velocity, which is meter per second, but it is squared. So we get kilograms meter squared second to the -2. Similar result to what we got before. A third approach would be to think of work done, defined as the product of force and displacement. If we start from this result, then we get force, newtons, and meters for the displacement. But as we saw earlier on, the Newton is equivalent to kilogram meter per second squared. So we can substitute that in here. And instead of the Newton, we write kilogram meter per second squared multiplied by meter. And we end up again with kilogram meter squared second to the -2. So in other words, it doesn't matter from where you start. If you stick to the correct working, you will end up with the correct result. We could also consider another example with power, defined as the rate at which work is done, so work done on time. As we know, power has as units watts, symbol capital W. And if we try to express these in terms of base units, we start by work done, which is in joules, divided by time, which is in seconds, or in index notation, we write it as joules multiplied by second to the power of -1. Now we have already found the equivalent base units for the joule, which is kilogram meter squared second minus 2, multiplied by second to the -1. Now when we have second to the -2 multiplied by second to the -1, we simply add the powers. So -2 minus 1 gives us -3. So this is the advantage of writing down the units in this form. So we end up with kilograms meter squared second to the -3. So these are the base units equivalent to the watt. SI units are sometimes used in conjunction with a prefix. This table is showing the unit prefixes that you will be using. The left-hand side is showing those prefixes for large numbers. These include giga, symbol capital G, mega, symbol capital M, and kilo, capital K. So we can have gigahertz, for example, megabytes, kilometers. On the right-hand side, we find those prefixes for small numbers. So we have centi, small c, such as centimeters, milli, small m, millimeters, micro, mu, this is a Greek letter, such as micrometers, nano, nanometers, pico. For example, picofarads. You will encounter such units next year. When working out a physics question, any of these prefixes must first be converted into the respective factor. So, if for instance we have centimeters, then centi corresponds to the factor 10 to the -2. So you have to make this substitution. So centimeters means 10 to the power of -2 meters. Similarly, millimeters means 10 to the -3 meters, and so on. So if, for example, you have the number 10.1 millimeters in a question, and you would like to insert that in an equation, all you need to do is to input 10.1 times 10 to the -3 meters. So there is a direct substitution for the prefix milli by the factor 10 to the -3. And all the factors are given here. So the factor corresponding to centi is 10 to the -2. All the rest are multiples of 3. So the powers are multiples of 3. Milli is 10 to the -3. Micro, 10 to the -6. Nano, 10 to the -9. Pico, 10 to the -12. On the other side, we have giga, 10 to the 9. So it's a billion, basically. Mega, 10 to the 6, meaning million. And kilo, 10 to the 3, meaning 1,000. Here we have some more examples. So suppose you have 20 micrometers. So that means 20 times 10 to the -6 meters. 100 gigahertz, 100 times 10 to the 9 hertz. Now here I would like to point out that if we had to convert 20 times 10 to the minus 6 in standard form, we find that it is equivalent to 2 times 10 to the minus 5 meters. This is the standard form notation. However, you should not worry about this. This is only used when presenting a final answer. So when dealing with numbers and equations, all you need is to ensure you're doing this substitution. Don't worry to shift the point in between the 2 and the 0. So the important thing is that you memorize each prefix in this table to the factor it corresponds to. Okay, so this is very fundamental in physics. Otherwise, you're not able to work out questions and convert the units properly. Now, it is important to note that in your calculator, you should have a special button for this. So suppose you need to input 100 gigahertz. So 100 times 10 to the power of 9. So you should find this button, EXP, or another one labeled times 10 to the power of x. So all you need to do is to input 100, press either EXP or times 10 to the power of x, and the power 9. And immediately you're inputting the number converted. It is also important to note that you have these buttons, E and G, that will help you to shift the point in multiples of 3. So these are a few tips on how you could use your calculator. We'll now discuss homogeneity. So an equation is said to be homogeneous with respect to units if the base units on the left-hand side of the equation are exactly the same as those on the right-hand side. You will encounter questions where you will be asked to check whether a given equation is homogeneous or not with respect to base units. This simply means finding out whether the base units are exactly the same on both sides of the equation. Let's take an example. So suppose you're given this equation, t is equal to 2 pi multiplied by the square root of m on k. And you are asked to check whether the given equation is homogeneous or not. First of all, you have to note the meaning of the symbols which would be given. So capital T means periodic time, m is the mass, and k is known as the spring constant, which is defined as the force per unit change in length in a spring. The most important thing is that its units are newtons per meter. An important thing to notice is this number here, 2 pi, which is called a dimensionless constant. So as we said before, dimensionless constants carry no units. So for this exercise, these can simply be ignored. Now the first step is to square both sides to get rid of the square root. So if we look again at the equation, so the units on the left-hand side would be seconds squared, because if we square capital T, we get T squared, so its units would be seconds squared. So the units on the left-hand side are seconds squared. Now let's check whether the units on the right-hand side will be the same. So in the numerator, we have the mass, which is in kilograms. So here we get the kilograms in the numerator. And in the denominator, we are given the units of K, Newton per meter. So kilograms in the numerator, Newton per meter in the denominator. Now, it is important to convert newtons into base units. We've already seen that these correspond to kilograms meter per second squared. Remember, F equals ma, mass times acceleration. So these are the base units for Newton. Then we still have to multiply by meter to the -1 and kilogram in the numerator. So kilogram in the numerator cancels with kilogram in the denominator. And here we have meter multiplied by meter to the -1. So here we have power 1. -1 is 0. So these cancel each other out. So we are left with second to the -2 in the denominator. So if we shift this into the numerator, it becomes second squared. So like what we had on the left-hand side. So the conclusion is that since units on both sides of the equation are the same, then the equation is homogeneous. So this is how you should handle these kind of questions. Now let's suppose that you are given the same equation, but without the factor 2 pi. You must note that we would still have obtained the same results. But obviously the equation is now wrong. The correct version is including the factor 2 pi. So this shows us that homogeneity is not something that determines whether an equation is right or wrong, but is simply an exercise to check whether an equation makes physical sense. In other words, we're saying that homogeneity does not imply correctness. However, if we know that an equation is correct, that implies that it should be homogeneous. Let's look at another example. Suppose we are asked to check whether this equation is homogeneous or not. So suppose now we're given S is equal to ut plus half at squared. I know that this equation should sound familiar to you because you've used it before. Thus, you should know that it is a correct equation and hence it must be homogeneous. But how are we going to verify this? We look first at its subject, which is the displacement, and we know that its units are meters. Now, this equation is telling us that when we add a quantity, which I'm calling term 1, ut, so this is a quantity, add it to another quantity, term 2, which is half at squared, we should end up with a number which is in meters. So this is only possible if term 1 is itself in meters, term 2 is itself in meters, such that if we add something in meters to another in meters, we end up with an answer in meters. So what I'm saying is that to check for homogeneity, when we have more than one term, so we have the plus sign or the minus sign in a formula, we have to check that each term has the same units as the subject. So let's do so. So term 1 is ut, u meaning initial velocity, so units meter per second, multiplied by time, which is in seconds. So we have second to the -1 multiplied by seconds, which cancels, so we are left with meters. Similarly, in term 2, half at squared, this is a dimensionless constant, half, so we simply ignore it. Then we have acceleration. which is meter per second squared, and time squared, which is second squared. So second to the minus 2 multiplied by second squared cancel, and again we are left with meters. So as I told you, we have something in meters added to something in meters, which gives us an answer in meters. So yes, it is homogeneous. So this is a particular case when we have two terms in the equation added together. In the last example, you are given an equation which you're told beforehand that it is a correct equation. So given that the above equation is correct, obtain the base units of quantity mu. So we're given that V means velocity, capital T is a force, tension, and we're given that the equation is correct. What does it mean? It means that we can assume that the units on both sides of the equation are the same. And the question is asking us to find the units for the unknown quantity symbol mu, whatever it means. The first step in such situations should always be to place the unknown quantity, in this case mu, as subject of the formula. So squaring both sides to get rid of the square root, we get v squared equals t divided by mu. Rearranging for mu subject, we get mu equals t on v squared. Hence, the units of mu are given by the right-hand side of the equation. So tension, which is in newtons, velocity squared, which is meter per second, all squared. So we convert the Newton into base units, mass times acceleration, remember, so kilograms times meter per second squared. And in the denominator, we square this, so we get meter squared, second minus 2. So we have second minus 2 in the numerator, cancelling with second minus 2 in the denominator. Meters in the numerator cancels with squared in the denominator, leaving us with meters. So we end up with kilograms per meter. So this is the answer. These are the units of mu. And it is correct, obviously, because mu in fact means mass per unit length. So mass on length should give us kilograms per meter.